Today, we're going to explore a pretty amazing technology that stores energy not with chemicals, like a regular battery, but with pure raw motion. But honestly, the spinning hardware isn't even the most interesting part. The real story is the hidden intelligence that makes it all work. So let's dive in.
Think about it. Every single time a train hits the brakes or when there's a huge gust of wind, all that energy is usually just gone, wasted. But what if we could actually catch it, store it, and then release it exactly when we need it most? That simple question right there is the key to a much more stable and efficient energy future. All right, so here's our roadmap. We're going to start with the big problem our power grid is facing. Then we'll meet the physical solution, this thing called the flywheel, before we get to the really cool stuff, the brain or the control strategy that runs the whole show. We'll even check out a few of these different strategies and then wrap it all up with why this technology is such a big deal for the future. Our electric grid is this constant, super delicate balancing act. Supply has to meet demand, like instantly. But now, with more and more renewables like wind and solar, which are famously unpredictable, that balance is getting a whole lot harder to maintain. And that volatility, it can cause all sorts of instability and waste across the entire system.
So, how do we fix this? Well, one really clever answer is this piece of engineering that acts kind of like a mechanical battery. So let's meet the flywheel.
At its core, a flywheel energy storage system, or FSS for short, is just beautifully simple. It's a really heavy, spinning wheel, they call it a rotor, inside a case with almost no friction. You pump electricity in to make it spin faster, and it just holds that energy in its momentum. Then, to get the power back out, you just slow it down, which generates electricity. That's it. Let's just walk through it real quick. First, power in. You get surplus electricity and use it to spin the flywheel up to some pretty incredible speeds. That's charging. Next, it just stores that energy by spinning for hours, sometimes even days, inside a vacuum. And finally, power out. When you need the juice, that spinning motion drives a generator, turning all that kinetic energy right back into electricity. Simple, powerful, and honestly, pretty elegant.
Okay, but having a crazy fast spinning wheel is really only half the battle, right? How does it know when to charge up, or when to send power back out, or how fast to do any of it? This is where we shift gears from raw physics to some really intelligent software. And this analogy just nails it. The flywheel itself is the muscle. It has this immense physical power. But without a brain telling it what to do, it's really just a useless spinning lump of metal. The control strategy? That's the brain. It's making all the split-second decisions. So what's this digital brain actually doing? Well, it's got a lot on its plate. It's managing the power flowing in and out, it's optimizing how to capture every last drop of energy, and it's regulating voltage to keep the whole grid stable. And maybe most importantly, it's constantly working to protect the physical machine from literally shaking itself to pieces. Now, not all brains think alike, and it's the same for flywheels. Depending on what you need it to do, engineers use totally different control strategies. So let's take a quick look at a few of these different thinking styles. So first up is a huge physical problem. As you spin a rotor faster and faster, it hits these things called critical speeds. These are frequencies where the whole system can start to vibrate like crazy because of resonance. If you don't control it, it could literally tear the machine apart. And here is where that intelligence is just absolutely crucial. A smart control strategy knows exactly where those danger zones are. It can carefully navigate the flywheel speed, accelerating or decelerating just right to pass through those critical speeds super quickly and safely. It basically programs the system to avoid self-destructing. We can kind of group these strategies into two main buckets. You've got your basic controls, which act like a simple reflex. They just follow a fixed set of rules. Then you have the advanced controls. These act more like a planning brain, constantly adapting to new information to figure out the best possible move. Let's look at one of each. On the basic side, you've got the good old workhorse, the PI controller. The easiest way to think about it is like a thermostat for power. It has a target, it sees where things are right now, and it's constantly making tiny adjustments to close that gap. It's simple, it's super reliable, and it's perfect for just straightforward charge and discharge jobs. Now for something way more advanced, an adaptive control strategy. This is a total game changer, especially for unstable situations, like a small microgrid trying to run on solar power. Instead of fixed rules, this brain actually adjusts its own settings on the fly. It learns from how the grid is behaving to bring stability right when things get chaotic.
So what happens when you have a whole farm of these flywheels? Well, you need teamwork. And that's exactly where a hierarchical strategy comes in. You have a master controller. Think of it like the coach that sees the big picture and gives the orders. Then you have individual slave controllers that manage their own flywheels. And they all work together to perfectly balance their power output and their state of charge, which is really just a fancy way of saying how full each flywheel battery is. So here's the bottom line. There's a right brain for every job. This chart kind of sums it all up. You've got your PI controllers for simple jobs, adaptive control for those shaky microgrids, and hierarchical strategies when you're managing a whole team of flywheels. There are even these super optimized strategies, like one based on something called Pontryagin's principle, that are designed to figure out the absolute most efficient way to use energy, say, in a moving vehicle.
So what's the big picture here? What does all this lead to? These complex algorithms and intelligent systems, they aren't just for some academic paper. They have a huge impact on our real-world energy systems. The real-world impact is massive. We end up with a more stable, more reliable power grid that can actually handle the ups and downs of renewable energy. We get to use all that green energy way more efficiently. We can capture energy that was just being thrown away before, like from a subway car breaking. And we can build stronger local microgrids that can keep the lights on even if the main grid goes down. And that's really the key takeaway from all of this. It's this perfect fusion of mechanical muscle and digital intelligence. These sophisticated brains are the invisible force that's making our physical energy infrastructure smarter, more efficient, and way more resilient for the future. Which kind of leaves us with a pretty fascinating thought, doesn't it? I mean, flywheels are just one application. If we can give complex machinery a brain that can sense, adapt, and optimize all in real time, what other incredible machines can we bring to life?